So, it's a special control seminar. It's the last one of this academic year. We'll start up again in September. Also, a special control seminar because it's the last seminar that our colleague Ian Hiskens is going to give before he retires at the end of summer. Now, I didn't say it's the last seminar he's going to give, just the last one while he's getting paid. Those of you who don't know, I met Ian 30 years ago when I was on sabbatical in Newcastle, Australia, where it turns out he was a professor, although I didn't know him. I met him at that time. And then years later, he moved to the University of Illinois, where a temporary appointment, where among other things, he co-taught a class with Dave Munson. He went to a full-time faculty job at Wisconsin. When Dave Munson came here to be chair of ECE and then dean, he and I knew each other. I was in Illinois, and we got to talking, and like, boy, it would be good to have some electric power people up here because there's all this grid electrification, all these renewables, and all this stuff, and we don't have any classes. And so we decided, well, maybe we better call up Ian and ask him to advise us on who we should hire. And so my instructions that day were to go home and ask Ian who we should hire and to tell him he could interpret that very broadly. And I'll leave the rest to him.
I could still remember a story with when we were interviewing, there's the usual kind of, Jim's telling us all the great things about Ann Arbor. We were walking around downtown and some homeless guy came up and started harassing us. And that was like, and Jim's like, this sort of thing doesn't happen around here. And the other thing is, like, neither Jim nor I have changed at all in the last 30 years. It's just the same as it always was, except there's no beach here like there was in Newcastle. Okay, so I'm kind of working on two different topics mostly at the moment. One's this load control aspect, aggregate load control, and the other is looking at inverter-based sources and controls. But next week there'll be two faculty candidates here, and they'll be talking about the inverter-based source and the controls of those types of devices. So I thought it probably fun to talk about the aggregate load modeling stuff. Both of those topics are motivated out of the growth in renewable generation. This is taken from a website that gives up-to-date output of what's happening on the Australian electricity market at any point in time. It's actually a couple of weeks old now, but it's typical of what one observes regularly. The light yellow is rooftop solar, the darker yellow is grid scale solar, the green is wind. And you can see that there's a fair amount of renewable generation that's happening in Australia. For example, rooftop solar, something like 30 to 40% of all houses in Australia have solar panels on the roof. Now, the climate is a bit more conducive. The sun actually does shine there, which makes it a bit different to Michigan through winter. And the electricity price is about 3 times what the price is here. So there's a lot of incentive for people to go and put panels on the roof. So that's kind of just a bit of a motivation. One of the aspects or issues associated with renewables is variability in the source. And the motivation for this talk is to look at being able to match the source variability by varying the load as well. So maintain that generation load balance in that sense. Oh, and I forgot way back at the start to acknowledge my collaborators and colleagues, Johanna and Giannis and Leaky and so forth. And there's people at other places as well, of course. So what we want to achieve is non-disruptive load control. So what does that mean? It's being able to establish some level of controllability from loads in a way where the consumer is not impacted at all. They're oblivious to the control action that's going on. So it's non-disruptive to the load. Load shedding, load control in a coarse kind of way has been around forever, but it is disruptive. On a hot summer's day, just when you want air conditioning to be running, it gets interrupted because there's peak load and they need to shed some of the load, and so that's quite disruptive for the consumers. But we want something that we can exploit without having without consumers having any knowledge of that. Some of the work that we've looked at is large loads like building, heating, ventilation, air conditioning type loads. I'm not going to talk about that today. I'm going to focus on harvesting controllability from large numbers of small devices. And we've put a lot of time into looking at thermostatically controlled loads, so air conditioning, refrigeration, heat pump type loads, and exploiting that to be able to levelize the variability in renewable generation. One can do play similar tricks with things like electric vehicle charging, and I'll talk a little bit about that at the end as well. And even though the forms of the load are vastly different, one can exploit some control strategies to make them kind of look the same. We'll talk a little bit about that. And there's a whole range of other types of loads that one could start to think about offering controllability, things like swimming pool pumps, dehumidifiers, and so forth. Types of loads where you don't really care if it runs right now, so long as it meets some criteria for running over a period of time. So swimming pool pumps, you don't care if it's running now, but you want it to run for a certain number of hours per day, those types of things. So I stole this slide from Johanna, but it really nicely illustrates the concept of non-disruptive control of thermostatically controlled loads. So if we think of the normal pattern of loading for a TCL, it's when it's off, the temperature is rising, and then it will turn on when the temperature reaches the upper level of the upper threshold of the hysteresis band. And then it'll be on for a period of time and cools the space down, and then it'll turn off again and proceed around limit cycle. We can introduce a control strategy that says, okay, we want this thing to run to, we allow it to be off and the temperature is rising. Before it gets to the upper threshold, we turn it on a little bit prematurely, and then we cool down. But before it gets to the lower threshold, we turn it off a little bit prematurely as well. The outcome of that is that we get these pulses of demand, and we can move those pulses of demand around. If you think about it, an individual pulse, well, what can we do with that? But when you aggregate it across tens of thousands, then you get a significant amount of controllability out of that. So that's the general idea at the sort of grassroots level of each individual device. But kind of stepping back, what is it that we want to achieve with ensemble load control? Well, we want to be able to meet competing objectives that the load has certain requirements that have to be met, but we want to provide some system service as well. And they are usually competing, as we've sort of seen. There's also this idea that load control strategies must be consistent with legacy operating philosophy. There's an enormous amount invested in the way that power systems operate now, and that's not about to change. It probably couldn't change. So we need to be able to have some overall load control scheme that is consistent with that higher level power system operational strategy. But we also need to be able to kind of access or send some signals out to the individual loads, and keep in mind this is large numbers of loads, tens of thousands, potentially millions as schemes grow. And to do that from in a centralized fashion where there's some central controller individually addressing all of those loads doesn't seem like it's a particularly practical outcome. So the idea that we have exploited is to say the load aggregator is broadcasting a common signal to all of the loads. So they're listening and receiving the common signal, and then they interpret that for their own individual circumstance. And each load makes its own local decision based on that broadcast message that's being broadcast to everybody. Come back to how different ways that works. We need to know what the resource availability is for the loads. Do we have lots of air conditioners available or very few air conditioners available? That kind of information. And so we can receive back from the loads at least a sample of the loads that we can build an estimate of the population from. So that's the load aggregated downwards to the load side. And then on the upward side, the aggregator is receiving signals from the system operator and also providing information back to the system operator. It might be availability or price, who knows what, but there's that interface on the system side as well. So that's the overall kinds of strategies that we've been exploring. Okay, so aggregation of TCLs, the way that we have kind of approached that is that we need to take into account the natural dynamics of the devices, the hysteresis-type process that described a little bit before. And the starting point for doing all of that is to build up a model that captures sort of the overall dynamics of the system. We've got lots of individual devices. We can't gain a whole lot from tracking every individual device. So we can aggregate all of that behavior together into what I'll show as a bin model. The temperature that's associated with each TCL is influenced by random perturbations, so things like doors opening, windows, so forth. So that introduces the model as noise, and we need to be able to take that into account. And then every device, every thermostatically controlled load has slightly different characteristics, different thermal properties and so forth. So we have a heterogeneous population. So there's the aggregation is inherently inaccurate, stochastic, but we can still make some use it both from an analysis point of view and introduced in a control sense as well. The gist for aggregating or building a model of a large number of devices is this bin model approximation. So we can think of this large population of thermostatically controlled loads. As we firstly normalize the deadband of these devices so that we can just kind of think of everything operating over that common upper and lower temperature band in a sense. And then we want to take all of the devices and map them into that common deadband. If we think about the temperature distribution of all those devices, then there'll be some stochastic distribution across large numbers of loads. We'll expect to see some distribution between the lower threshold and the upper temperature threshold over the spanning between those two. And also the devices will either be in the on state or the off state. So we end up with a probability distribution across the temperature band in the on state and the off state. And then we can approximate that distribution using effectively a finite element approximation. What that leads us with is this set of bands in the red case that describe the on state. So a TCL has a certain temperature and is in the on state, so that places it in one of the red bins that you can see there. And the other TCLs are in the off state with a certain temperature, so they'll fall somewhere in the blue bins. And so every device we can think of as lying in one of those bins, either the blue ones when they're in the off state or the red ones when they're in the on state. And so we can map the entire population of devices into a finite number of states, each state describing the proportion of the total population that lies within that temperature range. Okay, so that's the general idea. We have this linear representation now, which is giving us an estimate of the way that the population evolves around this limit cycle. And we can write that as a linear difference or differential equation. And the important thing to keep in mind is that the total population, all of the states, have to sum to 1. So each bin has a proportion of the total. When we sum up all of the bins, then that total population should equal 1. To ensure that it remains equal to 1, the A matrix has to be left stochastic matrix. What else? The steady state behavior of the overall ensemble is given by the eigenvector corresponding to the eigenvalue that equals 1, and convergence is given by the second largest eigenvalue. So kind of standard types of things for mapping the population. We can write an alternative formulation in terms of continuous time. In that case, the steady state behavior is given by the eigenvector corresponding to the 0 eigenvalue. So that's our model. We might have tens of thousands of devices, but we're mapping them into a relatively small number of states, a state associated with each of those bins. How many states? Well, if we don't have sufficient number of states, then we can find some artifacts associated with the modeling process. So in this particular slide, it's just looking at the same behavior, but with modeling the overall system with a different number of states. And it shows the most accurate case being with the total number of bins being 640. The actual experiment here is that we have a step change in the devices. So firstly, a homogeneous population. So there's no noise in this system and everything is identical. We assume initial condition with all the TCLs in the same bin, and then which is the last bin before switching on. So the dynamics are such that as time progresses, all of the TCLs switch on at the same time. Because they're homogeneous, they will then propagate through the deadband, and they will all switch off at the same time, and they'll propagate in the opposite direction and they'll all switch on. So one would anticipate coherent behavior if the model was behaving properly. Each of those devices draws a certain level of electrical power, and so when they all switch on, we would expect to see the power draw, the total power draw, increase, stay constant, decrease, stay constant. If we choose a sufficiently large bin number, so 640 in this case, then we do in fact observe that square wave. It's associated with the total aggregate power. But as we reduce down the number of bins, reduce the state dimension, become more and more approximate, what we observe is this beautifully damped behavior. And I've read papers where people are exploiting that beautifully damped behavior, but it's only damped because of model error, nothing to do with the true physical system. It's just model error. And so one has to be kind of careful about how to interpret the results. Have I chosen a large enough bin number, large enough state dimension to give a realistic view of what the behavior might look like? So that's one of the patches or one of the details that need to be carefully thought through. In this case, we've added, firstly, it's still a homogeneous population, but now added different levels of noise. We've used the most accurate model. So we're using the model that corresponds to the square wave that we have there with 640 states. That's the case in all cases. And so if we have zero noise, we recover exactly that square wave. But as we add noise to the system, it breaks the symmetry. So we're starting off with a homogeneous population all in the same bin. If you add noise, then that's going to spread that peak of devices. So that synchronization gets broken by the noise. And you can see that there, again, is a nicely damped behavior. But in this case, that's true damping. It's coming about from the noise that is part of the system. Okay, so the message is modeling is important and can sometimes bad modeling can be interpreted in the wrong way. So I want to move on and look at three particular control strategies. There's a whole lot of different strategies that have been proposed, but I just wanted to look at three. And the nature of the talk is to look at ways that they all have some amount of trouble. And so the message is we need to do careful analysis of these models and of these different control strategies, or we could end up with some unusual behavior. So I'll focus firstly on what's called transactive control. This was pushed heavily by the Department of Energy for a while, and then fortunately they seem to have given up on that. But it's a prices to devices mechanism where now the control strategy is one that is money related. So the idea being sort of given by this little figure here, that for air conditioning, as the temperature gets higher, my tolerance of that higher temperature, I weaken and I'm willing to pay more to receive electricity to deal with that higher temperature. So there's a mapping between the temperature and the offer price. If it's a high temperature, I'm very happy to pay more. If it's a low, if my conditioned space is already at a low temperature, I don't really care and I'm not going to pay so much for it. That's the general idea. So the temperature is evolving, as we've seen in this kind of normal hysteresis loop. Therefore, the offer prices that each individual is willing to offer is evolving in the same way. The market is cleared periodically. So what one ends up with is a period of continuous behavior where the devices are doing their thing, the prices, the offer prices are matching that. And then there's a point where the market is cleared, which is a discrete event on that system. So we have a classic hybrid dynamical system where period of continuous dynamics, then a discrete event, then another period of continuous dynamics. And it's kind of captured down the bottom here. This is the propagation forward of the bins and how things are evolving over a period of time. And then there's a clearing that happens to give me the restart effectively. So this is the restart and the reset, and it's price dependent. So depending on what price is being broadcast out will alter the dynamic behavior of the overall population. Oh, and the kind of important thing is that all TCLs with an offer price above the clearing price get switched on, and all TCLs who have offered less are switched off. And that's driving this reset matrix here. Okay, so what does that end up doing to the overall population? Well, if the price is low, the top one is, indicates a clearing price of 10 units, then that's going to lead to a bunching up of the devices at the cool end of the hysteresis band. Electricity is cheap. People are happy to be utilizing that electricity, and it leads to this kind of bunching up down the far end. The population of off states is shown in blue, the on states are shown in red, and this is the distribution at the instant prior to the reset event. So we end up with a limit cycle happening, and this is what things look like just before the instant before the reset happens. If we transition down to the bottom, prices are now high, up at 30 units, and accordingly, the people are less willing to cool their space, and so the overall population of TCLs is migrated towards the top end, the hot end of the schedule. And in between, as the price varies, we can see there's that migration from one end to the other. One of the interesting things is that if you introduce a dither in the price, then you can actually synchronize all of these devices. And this, I'll show a little video if it works. I won't show it if it doesn't. It's one of the joys of Microsoft that it kind of works every other time, but not when you want it to. Okay, we'll forget that. It was working before. Anyway, the idea is that as the price dithers, the devices respond to that. They kind of get pushed from one end, they get pushed from the other. The nice little animation shows it, but it's not going to yeah. It's a case where you can have, when you switch between two stable systems, you can end up with an instability out of that. And it's kind of counterintuitive. You think if I've got two stable systems, I should be able to switch between them and still maintain a stable outcome. Well, that's not necessarily the case. And this is a situation of that form where we're switching between two stable cases. And in doing so, we end up with a synchronization. We can't go unstable because there's a finite population. But what does happen is becomes totally synchronized. Okay, moving on to probability-based switching. This is probably the form of control that we've exploited most, and Johanna was leading a project with ARPA-E that this was one of the main control strategies that we were interested in. So in this case, we have a bin model that's enabling us to do a one-step ahead prediction. We have a reference signal that we want to track, and we obtain an estimate of the population, pass that one step ahead through A, look at the power output through the C matrix, and obtain this difference between what's desired and what our estimate is of the total power demand. So that mismatch drives this, is proportional to and drives this U vector, which is distributed out to the total ensemble. So the scalar is assigned to the bins using weighting factors. And on the next slide, I'll show kind of the impact of choice of weighting factors. But depending on the weighting factors, you can end up with a non-negligible impact on the overall form of behavior. The really cool aspect is it meets their requirement for being able to broadcast out to all of the loads a common signal. So send out to all of the loads a probability number that's associated with each bin. So if we have n bins, the length of the vector that is distributed to everyone is going to be n. Locally, the TCL knows what its temperature is and knows its on-off status. So using those two pieces of information, it can work out which bin it lies within. And given that it knows which bin it lies within, it can pull off that probability number and then run a random process to decide should it switch its status or should it not switch its status. So it's a really nice, simple way of achieving this idea of blasting out a common signal to everyone, but allowing the individuals to operate in a way that is meaningful for that particular device. One of the things that one does have to be a little careful about, though, is in choosing this, in choosing the weighting factors that we want to distribute this control signal to. So this little experiment, it's just a step response in the power reference. And it's just saying, okay, I want to, my nominal power is running at 1 per unit in steady state. And then I want to just step that up by a certain amount. So in kind of our intuitive thinking of how we would like controlled devices to respond is in terms of I apply a step response, I would expect to see some nice first or second order response tracking that step. This control scheme, well, the TCLs, the ensemble of TCLs doesn't behave like that. If I introduce a step, then I immediately change the status of a certain number of devices, and I'll immediately see a step. But if I don't do anything further, what I'll see is this relaxation of the total demand. So what do I get? Here's my initial condition, a value of per unit value of 1. I get my step up, but then depending on how I've assigned the weighting factors, under all conditions, it will return back to that value of 1. But depending on how I assign the weighting factors, it will quickly return back to a value of 1, or it might take much longer. So if I choose to provide much higher weighting to the ends of the hysteresis band, so either the hot end or the cool end, then I'll see this fast relaxation back to its original value. If, on the other hand, I choose to weight the bins that are in the middle, either in the middle of the off group or in the middle of the on group, if I give them a higher weighting, then I'll see this sustained step for a longer period of time before it eventually collapses back. And these responses are just a feature, an aspect of what's going on with the TCL. So if we think of devices that are close to the end, and we're asking for more power, so we're wanting to switch from the off to the on. So let's consider devices that are off, but near the top of the higher temperature end of the deadband. So we're going to switch some of those down into the on, and that gives us this initial response. But now, because we've switched them prematurely, when they would normally have cycled through and back, hit the top end of the temperature deadband and progressed, switched into the on, those devices have already switched. And so there's kind of a gap in the population, if you like. And so after some time, it's as if we never did anything. Those devices that were prematurely switched would have switched anyway. And so we lose the temporary gain in power that we were wanting and see this response back down. Choose something in, and there's a similar argument at the low end as well. If we switch at the lower end, then they'll soon switch off again, and we see that similar response. At the higher end, they stay in their altered state for longer, and therefore they give a power demand that remains high for longer. If we choose a uniform distribution, so we're wanting to switch from off to on, we choose the same proportion of devices from every bin, what we see is this straight line, because now as they kind of would have hit the top, they switch down. And so there's this progression of reduction in the loads, the extra load that we had obtained. So a step response doesn't look like the usual form of step response, and the non-linearities in this model have to be carefully managed to be able to deal with that. The other thing with this model that we've recently discovered, when we're tracking a signal that's like, in this case, 10 cycles per hour, we get quite good tracking out of that. But as we speed up the reference signal, then there's an emergent form of behavior that we're observing. It has something to do with what's called the lockout phase, where when a device turns off, TCL turns off, you can't immediately turn it back on again. But there's more complicated things that are going on there as well. So it's an open question, but it does highlight the fact that we're dealing with a nonlinear system. And when you're dealing with nonlinear systems, anything can happen. Well, not anything, but lots of unusual. The third and last form of control is set point variation. So in this case, the idea is to move the set point and keep the upper and lower bounds of the hysteresis loop symmetric about that set point. So as you move the set point up, the deadband moves up with it. If you move the set point down, deadband moves down. And the control strategy comes about, as mentioned there, that we get an increase in load by lowering the set point. When we lower the set point, we cause devices to switch on prematurely and so forth. So we're moving the entire set point up and down, and that gives us the control in this case. One of the places where we've used this is not TCLs at all, but electric vehicle charging. And so in this little plot here, we're saying, well, we've got a vehicle that plugs in at, it's not showing up, okay. Vehicle that plugs in at this point here, and it needs to be fully charged by this time up here. So let's draw a straight line between those 2 points. We have a certain amount of energy that needs to be delivered in a certain time. But rather than charging along that straight line, which is the blue line here, let's put a hysteresis band around that, such that I charge, can't this work? Maybe that works. Yeah, okay, that works. Okay, so I charge for a short period of time until I hit the upper deadband, and then I stop charging until I hit the lower deadband, and then I turn on the charger and off and on and off. And so out of that comes this sequence of on-off pulses. So the charger is on for a period of time, it's off for a period of time. As if I move that deadband around, I can move the sequence of pulses just a little bit, but when aggregated across a large number of devices, it gives me the similar form of controllability as we've had with TCLs. So in this lower figure down here, we use that scheme to track a fairly weird desired demand, but it's actually a demand that shows sort of the overall load demand, but then it's got wind power variation on top of it. So the dashed red line was the desired demand, and we were able to track that quite well using this control scheme. And this is the shift in the deadband was not particularly extreme. Doing that kind of thing, just moving a little bit, but aggregating over a large number of electric vehicles gave us that level of controllability. Okay, so that's encouraging. What's not encouraging is that this is, again, a hybrid dynamical system, and it exhibits some interesting forms of behavior. So we're dealing with, again, a little experiment. We're putting this triangular wave into the bin model associated, well, with 2,000 electric vehicles, each with a charging power of 4 kilowatts. The model is quite accurate under this condition shown here. What we observed, though, is we vary the period of the oscillation, we get these period adding bifurcations happening. So for a period of 30.8 minutes, so it's oscillatory with period 30.8, that's the outcome. When we reduce the period to 24.4, we get a period 2 response. So there's clearly a nonlinear phenomenon that's going on there. In fact, what we observed, this was the first case, it was period 1. red dashed line is the second case, it's period 2. In between there's actually a region of chaos. And as you further increase or decrease the period down along here, there's more chaos, it breaks into period 3, there's more chaos, it breaks into period 4. So these are what the period 3 looks like, what period 4 looks like, and all fun things like that. Of course, in the region where there's chaos, in region where there's periodic behavior, the model gives a good representation of the simulating the 4,000 devices, electric vehicle charges, or whatever the number was. But when we're in a period of chaos, chaos is infinitely sensitive to initial conditions. And so, as you would imagine, it's very hard for a model, a bin type aggregate model, to be able to capture what's actually going on with the overall with the overall chaotic form of behavior. So the model breaks down, that has consequences for using that model in control schemes and so forth. The chaos, so this is still an active area. Work was done a few years back, but we've got some new tools to play around with things. And so it's likely, it's not fully convincing yet, but it's likely that the periodic behavior or the bifurcation behavior is due to what's called grazing or border collision bifurcation, where you have, under certain circumstances, the trajectory misses a switching surface, but under other, it encounters that switching surface and a new form of behavior emanates from that. So there's a rich form of response that's possible here. So, in conclusion, that significant actuation can be achieved through coordinating non-disruptive control of highly distributed loads. Well, and hysteresis-based control of electric loads may exhibit rich forms of dynamic behavior. So, and of course, we should mention the sponsors of this work. It goes back a number of years. It's been funded by ARPA-E, Department of Energy, and NSF for years. But Jim, I'll finish the sort of technical part, but Jim gave me leave to show one extra slide, which is the real reason I'm retiring. So that's the real reason I'm retiring. There's a whole bunch of grandkids in Australia just waiting for us. Anyway, and I haven't even met these two yet. They were born in January and February, and it's kind of hard to travel during semester, but we'll get this. Okay, that's it.
Any questions?
Very nice talk, first of all. I'm curious about, okay, so all this is predicated on a bin model and a discrete time dynamic model. Does anything change when you do it with continuous time instead?
No, it doesn't. So when I do most of my bifurcation chasing work, it's in continuous time.
The follow-up to that is, has anybody looked at something other than finite element in types of approximations, using other basis functions that are perhaps not bins, and do you still end up with the same artificial damping effect, that sort of thing?
So the kind of the basis for the modeling is Fokker-Planck model representation, and then discretizing from that. As far as I'm aware, that's been the process for these sort of ensemble representations in this kind of what we want to do. But Johanna, do you know of other work?
Just thinking, like, so, I mean, you're using these bins as basis functions, but you could, of course, use anything you wanted as a basis function for the Fokker-Planck equation. So, anyway. All right.
There's certainly been a few people. Duncan did some work. The work actually goes back to Roland Vennema long time back. There's been some work done in Europe, but it all kind of ends up in the same bin type of representation.
Other questions?
About the slide where you first showed the big model. The band is represented by theta over 2 and plus or minus that. And it's for aggregated TCLs. Does it matter what the set point, like, does that assume a constant set point temperature across all aggregate TCLs to set that dead band? And does it matter if you alter the set points in the TCLs?
It does matter, and it also matters in the changes for the ambient condition and so forth. And so Janus has kind of a suite of different A matrices that describe behavior under various different forms of conditions. The idea being that in the overall control scheme, we would be like measuring the ambient temperature, and depending on what that was, we would use the appropriate A matrix that had been learned previously and maybe update as well. Yeah.
I have what might be actually a difficult question. Could you go to the next slide?
Yeah.
Well, what are their names?
Yeah, I'm not going there. And Lincoln, Ariella, Finn, and Eden.
If you're right.
Don't ask me birthdays. You know, I mean, I used to know what their birthdays were. No, these two, they were pretty recent, like 31st of January and 8th or 9th of February. It was more than a month ago, I can't remember.
All right. Well, questions, let's thank Ian again and wish him a happy retirement.
I need someone to ask you.
I figured notes on your PowerPoint slides. So I can see that everybody will scan. Yeah, you did something over the summer.
My parents. Supposed to be April.
Are you ready now?
I've been waiting for months.
Same thing, it's just small, it's not even close.
It can be, yeah. Down. See that. December itself. I think it's $80.90. Like so, it's for 80 or 90 Okay. But there's a practical.
I'm discussing on Monday. Probably second last, because last day of classes. So I asked them, will they attend if I have? And they said they will. But I'll ask them again this week. We'll see what happens. I want to hold one of the last day of classes. I want to tell them there's so much more out there. Like I can tell them a lot of like general stuff, general subject that I know. So, and there are like students in there who are such students who are starting graduate courses in fall. So a lot of them have asked me what courses should I be taking and things like that. So I want to leave it like I want to leave it as a general advice session. It would be very nice. Yeah. I'm gonna show. Have you seen Brian Douglas's map?
Yeah.
I'm gonna show them that. I'm gonna show them that because I'm pretty sure they've not seen that. So I'm gonna show them that and I'm gonna say, you know, this small bit here, but there's all of this up there. Like provide a bit of perspective. I think it'll be useful. I think it's very necessary. See, I will take it fun. I'll be a little like this one. I'll wear an engineering alumni t-shirt. It's my last day of class, last semester. Like follow back to your, so last meeting, we kind of, I really enjoy the group meetings, like, it's been a lot of fun. It's something I'm gonna miss, for sure. I mean, this semester has been fun. I've had multiple opportunities. Carolyn, all of this was like, it was fantastic. That was something I thought I didn't have before. I will have that UAC as well, and
So that chart showing.
more, I feel I didn't take advantage of it much here in my first, like, in the first year at least. I was a little lost a bit. But now that I'm.
गाड़ी से जाते हुए
I just want to get it done. I want to settle housing. I want to go.
Yeah.
So when you
That's your own-
for this beams, like, sorry, I missed it. How big are these beams?
Oh, yeah, no. So if you want to actually, you have to use a large number. Why is the last?
These are in temperature, right? So you have the boundaries about what is considered high and low, and then you break it to 6 Kelvin base, is that what you're saying?
Well, if you think of it being like 2-degree dead band, then that's divided with 300.
The 2 degrees band is 300.
Yeah,
Bins.
it's 300 bins on state, 300 bins. You probably, on this, depending on what the study.
Because I'm just thinking, when they call, I mean, we have the standard temperature control things, right? I mean, they have a dead band that it's more than about 1 degree.
Yeah,
So this one would need something that is beyond.
the issue with the standard dead band is that the inaccuracy is enormous.
Right,
Yeah.
because of the temperature calibration, right? I mean, our temperature sensors are not calibrated to more than, 1 degree accuracy, and then dead band on top of that of the air
Yeah.
conditioning system.
But the dead band, like the inaccuracy of the set point, you can manage.
Sure.
If the dead band was always exactly 2 degrees wide. You could probably. We've been doing a bunch of stuff for Khan Street, and Yarmouth has actually been out there. Working with the guys to be able to get perturbed and observe type things. When does it turn on? When does it turn off?
Right. Because that's what I was thinking, like in a real system, it would be very hard to implement anything like that.
So the big problem is lots of these houses have these nest thermostats or running type thermostats, but they don't give access to the API. So all of the information we need is in the box, but we can't get it out because corporate rules. So we've had to add our own thermostats and place them in appropriate places in the house and duplicated all of this other stuff. It hasn't worked.
Yeah. I actually tried to do an ME360 homework problem like that.
Yeah. Not the way. Yeah, okay. Oh, yeah, okay. Well, that's that. Guess I'm still live on. Oh, yeah, I don't know.